So thermal energy storage. So I've got some props here, but I want to just put things in context before I go straight to it. So as many of you know, about 41% of the world's produced energy is used to heat, power, and cool buildings. That's true for the United States. IEA says it's similar for the built environment around the world. So that's heating, power, and cooling of buildings. And they account for about one-third of world greenhouse gas emissions, the energy required to power, heat, and cool buildings. The power and cooling component is usually electric, and so easily, there you go, sorry, and is so easily convertible to renewable, and is easily convertible to electricity that's clean, right? Except in district energy systems, and most of you probably know what district energy is. Instead of buildings having standalone heaters and air conditioners at our universities, I'm sure most of our universities have this, you have a central energy facility that can supply heat and power to the buildings, or heat, power, and cooling. Cooling's usually in the form of chilled water, right? And heat, unfortunately, in the United States is almost always steam. And some universities also generate power through cogeneration, or et cetera. So on those district energy systems, often the cooling isn't made with electricity. It's partial electricity and partial steam from the cogen unit. So conversion of university district energy systems, or city and airports and so forth, sometimes it's a lot more involved than just finding a way to make the heat electric and going with clean there. But that's the point. Getting this sector of energy to renewable, to clean as it were, the big challenge is the heat part. It's far more efficient, conventionally thinking, to use fossil fuels for that. You know, who at home has an electric dryer versus a gas dryer anymore, electric furnace versus a gas furnace, right? For those reasons. But in the big industrial settings and somewhat at home, really heat pumps are the most energy efficient way to produce low-grade heat. So a heat pump, if it takes 1x of fuel, and that can be gas into a grid power plant, for instance, to make a certain amount of heat, a boiler or hot water generator that's 85% efficient takes twice as much fuel. And an electric radiant heater, even though it's 100% efficient in the conversion of the electricity to heat, the fuel required to make that electricity is 5 times the electricity that's required to put in a heat pump to get you that same amount of heat. So heat pumps are definitely the most efficient solution to the heat sector of providing a building's heating and hot water. And it's also the path to sustainability because it's an electric technology. So all that plays into the fact that if we're going with an electric system and we're using heat pumps that produce hot and cold, then thermal energy storage becomes a great addition to such a system. Just by itself, thermal energy storage, and here's a little diagram showing the typical kind of thing, but if you have a sine type wave of heating load or cooling load at a campus or in a building, you know, because of the daily occupancy and so forth, if you were just to provide enough equipment to do the maximum amount of work, you might have, say, 20 units of chillers or 20 units of boilers. But if you can store some heat and base load those equipment and run them level 24/7, then you can get by with probably 2/3 the amount of capacity. So a tank is a lot cheaper to build than a boiler or chiller, and a lot cheaper to operate and maintain. So thermal energy storage is quite useful just from a basic engineering viewpoint. And almost all district energy systems that use chilled water around the country now have thermal storage fitted to it. Some are just recently coming online in the last 5 years, believe it or not, with thermal storage, but it is pretty prevalent now. There's both ice and cold water thermal storage. Cold water is far more efficient than ice. It takes about 25% more energy to make ice to store cold, as it were, or the absence of heat, as it does cold water. The capital cost, like I say, is about 5 times for the boiler and chiller, so hence just economically it pays to have thermal storage. But the big benefit of thermal storage goes beyond just cheaper capital and operating costs. It's load shifting. So obviously people that have thermal storage can operate their equipment and do off-peak, as it were, in a conventional peak scenario, and draw their electricity at night. And so it's cheaper, and it helps with their overall profile on the grid. So great benefits to that. But as we now move to electrify electric heating and cooling, we now have hot and cold. And so it'd be really good to store some heat too, just like we're storing chilled water for our systems. If we store hot water, we get all the same benefits of thermal storage and storing cold with load shifting. And we get an additional benefit, which is heat that would normally be lost can be saved and used at a later time. So for instance, if you have a high cooling load in a summer day, you would normally just exhaust all that heat through cooling towers. But if you had a cool night, if you live on the coast or the desert somewhere, what if you could save that heat instead of throwing it out evaporative cooling towers and then use it at night for your heating? So thermal storage in the presence of both hot and cold should be both hot and cold thermal storage. Those are the big benefits of it. So is this potential for storing and reusing heat prevalent around the country, or is it just something that's available in mild climates like Stanford? We get that question all the time. So we've done some studies with the help of some other universities, including a large research university in New England, a large Midwest research university in Illinois, my old stomping ground, UC Davis. And we found that in every setting, in a district energy setting, greater than 50% of the annual heating and hot water load for that university could be made with recovered heat. So heat pumps, as the most efficient way to make heat, the most efficient way to use a heat pump is to first use recovered heat. So if you have a cooling process already going on, which is collection of unwanted heat and discarding it, well, if you can use that heat with your heat pump to provide heating and hot water for your system, then that's the best first use of a heat pump. The next best use is to extract heat from a water body or the ground in lieu of burning fossil fuel for all these reasons. So preferentially, if I was designing a system for a university anywhere in the United States, I would first use the recovered heat from my chilled water system on my campus, and second, augment it with ground or lake, river, or ocean source heat exchange using the heat pump to extract heat from those places to provide the remaining heat I can't get from heat recovery. You do all that and you have a fully electrified system that you can move. So maybe that's the 80% conversion, or maybe this is part of the 20%, but that's the long-term strategy if you don't want to do carbon capture and storage of burning fossil fuel on your campus or your city or wherever, or if you don't want to try and go the sustainable biofuels route. So given that, when you have both hot and cold thermal storage, it becomes a little more difficult for humans to operate that optimally. If you can imagine going into the control room of a plant like that in the morning, trying to predict what are my loads going to be hour by hour for the next day or days, and when should I operate my heat pump to put things in storage or take them out and juggle the hot and cold, it becomes a little bit of a mathematical challenge. Now we've shown that human operators can do that. They can meet the loads in a system like this, but the computer can do it a lot more efficient. So we invented a program based on model predictive control where we're looking hour by hour constantly 7 days in advance, so as to always grab a weekend since the load patterns change, predict what the loads are. We predict what energy prices will be. We have a deregulated electricity market in California where day-ahead prices vary by hour. And so based on the distribution of electricity prices and our projected loads, the computer finds the optimal way to dispatch the plant, when to do heat pumping, heating, cooling, when to take and put from thermal storage. What that program does, and we've proved this through a training exercise with our new system at Stanford, when we didn't have MPC and we just had our operators go through a sample year and show us how they would run the plant, we gave them a set of loads, 8760 loads of heating, power, and cooling, and said, starting from January 1 at hour 1, dispatch this. Show us every hour what you'd turn on, turn off, and take and put from thermal storage. And the results were that we normally have an 18 megawatt minimum load and 31 megawatt minimum background building electrical load on campus. So the additive work with humans dispatching, because this plant's about a 20 megawatt plant. If you turned everything on, it could draw 20 megawatts compared to the building load of 18 to 31 megawatts. So if you just let humans turn it on to try and meet loads, the result was our peak went from 31 megawatts to 43 megawatts, load factor of 72%. Let the computer do it, 7 megawatts less peak throughout the year and an 87% load factor, and over 10% savings in energy. And in our case, that's between $500,000 and $1 million a year, lower energy cost due to demand and commodity pricing. So you not only get a much more efficient footprint on the grid, you save a whole lot of money. So to summarize all the benefits, I would say it's probably most practical to electrify heating, cooling, and power for buildings. Deploy heat pumps to provide the heat component of it. Use recovered heat first, ground source heat exchange or water source heat exchange second. Employ both hot and cold thermal storage in the form of water, not steam or ice. The temperature band in buildings is like this. You don't need steam and you don't need ice to heat and cool buildings. It's overkill. You're wasting a lot of energy producing these very high or low energy systems for a bandwidth like this. And the interesting part was when we had cogeneration, we had 12,500 tons of ice chillers and ice storage, and we had another 10,000 tons of conventional water chillers. When the cogen plant went down for maintenance, there was a grid impact of Stanford of 46 megawatts. We have now electrified the entire system, and our impact is 36 megawatts. Who thought possible that you could electrify an energy system for a city or a campus and actually lower your impact on the grid through use of thermal storage and smart controls and software? So that's in a summary where I see the big benefits of thermal storage. It's cost effective, so I don't think there's an economic barrier. The only barriers I've seen is people don't understand its value. There's some complaints of the size. So where are you going to fit a big tank on your campus? But if you looked at a map of Stanford, a picture of Stanford, you'd have to look quite a bit to find our tanks. In the grand scheme of things, it's not that much space on campus to enable a transformative change in your campus energy system. So excuses that we just can't find the space, well, there's always space. I think USC put it under their football field. You know, so you can put it underground. Others use big above ground tanks. Stanford went half underground and half above ground for architecture. So there's usually a room. So I think the biggest barrier is that perception of where you can fit it in architecturally and space-wise on your campus. But everything else points to real good value from it, and there's not too many other barriers. This is the thing that we couldn't find in the industry. We couldn't find any software that could do this kind of thing. So we had to create it ourselves. And now Johnson Controls is out turning it into an industrial type thing. And a few other universities, Kent State, Arkansas, and others are starting to use it too, Ford Motor Company. But that proved a real benefit of savings. And it can be used at any existing district energy system. So even in the system without thermal storage, knowing what equipment to turn on based on the equipment efficiencies of the plant, you can deploy the software and probably see a big savings in energy and a much lower grid footprint than you would without it, because you know the computer can just do math so much better than humans. If you have a plant with 10 different kinds of pieces of equipment of different capacities and performance curves, humans can't juggle that stuff. The computer can do it like that. The last interesting thing is currently we optimize based on the best economic combination of demand charges and commodity prices. But a question about, like, if we went all PV, we could actually use the software somewhat for generation following. So if there's some real value, if Stanford went 100% PV, we went about 50% PV. We recently, when we set the system up and went electric, we did a PPA with SunPower for about 54 megawatts of new PV down in Southern California. So right now we dispatch based on what the market prices are for economics. But if we want to just follow our generation, we could to some extent. We could just tell the computer, instead of optimizing for load factor and commodity, try and use as much power as you can when the PV is produced. It's just a criterion, the computer does it. So you can't match it totally because this background building load is typically not dispatchable. It's not controllable. We're trying to get some control of that. But unless you have some really big pieces of equipment like a half a megawatt MRI or something, there's not a lot of dispatchable electrical load in background in buildings. So that's kind of a constant that we're working on to fix. But with your heating, cooling, and for a university, probably half to 2/3 of the total energy load for a dense built environment, whether it's a campus, a downtown area, or whatever, then you can control that 2/3 energy in a number of ways to get the electrical grid footprint you want. Follow market price signals if they transmit what we're trying to achieve, or just structure it to whatever you want to achieve to the extent you can. And that concludes, I think I'm done.